Pick a number, any number. A big one, 1,000 digits, 2,000. Is it prime? For 2,000 years, mathematicians had exactly one tool for this question. Take your number, divide it by every smaller number, and check if anything goes in evenly. Trial division. Eratosthenes used it in 250 BC. Fermat used it. Euler used it. By the 1970s, computers were running it on numbers with hundreds of digits, and they were drowning. To check whether a 1,000-digit number is prime by trial division, you have to perform roughly 10 to the 500 divisions. The universe has been around for about 10 to the 17 seconds. There is no way. But cryptography needed primes, big ones. 1,000-digit primes were the foundation of RSA, the algorithm holding up internet banking. So mathematicians started asking a different question. Forget factoring. Just answer yes or no. Is this number prime, without telling me what its factors are? Pierre de Fermat had given them a hint 3 centuries earlier. If n is prime, then for any number a to the n is congruent to a, modulo n. It's a sieve, compute a to the n mod n. If it doesn't equal a, n is definitely composite. If it does, n is probably prime. Probably. There are weird numbers, called Carmichael numbers, that fool this test for every base a and pretend to be prime forever. The smallest is 561. 561 is the product of 3, 11, and 17, but Fermat's test calls it prime no matter what base you try. That was the state of the world. Probably prime tests, fast but uncertain. And one open question. Could you build a fast test that was certain? In 1976, Gary Miller and Michael Rabin patched Fermat's test. Their idea: instead of just checking a to the n mod n, look at the path the powers take getting there. Write n-1 as 2 to the s times d. Then check the sequence a to the d, a to the 2d, a to the 4d, all the way up to a to the n-1 over 2. For a prime, this sequence has a very rigid structure. The only square roots of 1 mod n are +1 and -1. For a composite, there will be witnesses that violate the structure. With enough random a's, you can drive the false positive probability below any threshold you want. Run the test 40 times, error rate 1 in a trillion. Solovay and Strassen had a similar test using the Jacobi symbol. Edelman, Pomerance, and Rumley built one based on cyclotomic numbers. By the 80s, there was a small zoo of probabilistic primality tests, all running in polynomial time, all with vanishingly small error rates. Practical cryptography was solved. RSA shipped. The internet got encrypted. But the theoretical question stayed open. All these tests were probabilistic. They returned probably prime, or conditional on the generalized Riemann hypothesis, definitely prime. Take away the randomness, take away the unproven hypothesis, and the question that started this whole field, given n, is it prime, yes or no, was still officially unanswered in polynomial time. For 30 years it sat there. Some of the greatest computer scientists of the 20th century took shots at it. Edelman, Pomerance, Goldwasser, Killian. They got close. They never closed it. By the late 90s, most experts assumed deterministic polynomial-time primality testing was probably possible, but probably hard, and probably not coming anytime soon, the opinion was. Maybe in a few decades, with enough new analytic number theory tools. Then in August 2002, an email arrived in a few inboxes around the world. The email came from the Indian Institute of Technology in Kanpur. It contained an 8-page paper titled, quote, "Primes is in P," end quote. The authors were Manindra Agrawal, a professor of computer science, and 2 of his students, Nirag Kayal and Nitin Saxena. Both had just finished their bachelor's degrees that summer. The paper claimed an unconditional, deterministic, polynomial-time algorithm for primality testing. No randomness, no unproven hypotheses. Given n, the algorithm returns prime or composite in time that grows like a polynomial in the number of digits of n. The 30-year-old open problem was over. Within 48 hours, the paper had spread to every theoretical computer science department on the planet. People posted that they might have to revise their lectures. Carl Pomerantz, one of the people who had worked on the problem for decades, read the paper, found a small improvement, and emailed it back the same day. Hendrik Lenstra read it on a flight. Within a week, every claim in the proof had been verified. Within a month, faster variants were in circulation. The two students were 22 and 23 years old. Neither had a PhD. The paper they wrote is, by any measure, one of the most beautiful pieces of mathematics produced this century. What it actually does is build the entire algorithm out of one identity. 1. A polynomial congruence so simple you can fit it on a single line. Everything else, the bound on R, the running time, the correctness proof, falls out of that single identity. And that identity is sitting just above Fermat in a place nobody had thought to look. Here is the identity. If n is prime, then for any integer a coprime to n, the polynomial expression x plus a raised to the nth power is congruent to x to the n plus a modulo n. Read that twice. We're not raising a number to the n, we're raising a polynomial, x plus a, to the n. And the claim is that nearly every coefficient that comes out of the binomial expansion is divisible by n. The binomial coefficient n choose k, for k between 1 and n minus 1, is divisible by n exactly when n is prime. So everything in the middle vanishes mod n, and you're left with x to the n plus a to the n. By Fermat's little theorem, a to the n is congruent to a, so the right side becomes x to the n plus a. Identity proved. The remarkable part is the converse. Unlike Fermat's original little theorem, which has those Carmichael holes, this polynomial version has no holes. If x plus a raised to the n is congruent to x to the n plus a modulo n, then n must be prime, period. No pseudo-primes, no exceptions. So we have a deterministic primality test. Compute x plus a to the n, check whether it equals x to the n plus a mod n, and you're done. There's just one problem. The polynomial x plus a raised to the nth power has n plus 1 terms. To compute it, even mod n, we need to track every coefficient. That's n coefficients, each up to n in size. Total memory order n times log n. For a 1,000-digit number n, this is 10 to the 1,000 bits of memory. We've made things infinitely worse. The test is correct, but it's exponential. What Agrawal, Kayal, and Saxena needed was a way to truncate this polynomial identity, to keep only a few of its coefficients without breaking the correctness. They found one. Their trick is to work modulo a small polynomial. They pick a value r, the right r, to be chosen carefully later, and reduce everything modulo x to the r minus 1. In the polynomial ring of integers mod n, modulo x to the r minus 1, every polynomial collapses to degree less than r. Multiplying x by x to the r minus 1 gives x to the r, which is congruent to 1, so x to the r equals 1. Powers wrap around. The polynomial ring becomes a small, finite, manageable thing. The full Agrawal-Kayal-Saxena identity is, if n is prime, then x plus a raised to the n is congruent to x to the n plus a modulo x to the r minus 1, and modulo n. The same identity as before, but now living in a ring of size order r times log n instead of n. For a clever choice of r, of order log to the 5th of n, this is genuinely polynomial. We can compute the left side using fast exponentiation. We can compare it to the right side. The arithmetic is small. So what's the catch? The catch is the converse. With the original full identity, the converse held automatically. If x plus a to the n equals x to the n plus a exactly, then n is prime. But after we mod out by x to the r minus 1, we've thrown away information. Composite numbers can now satisfy the identity by accident. They can pretend to be prime in the truncated ring. This is the entire difficulty of the AKS proof. The polynomial congruence, mod x to the r minus 1, is necessary for primes. That part is easy. The question is, how many A's do we need to test? If a composite n manages to fake the identity for one A, that's not surprising. If it fakes it for 10 A's, maybe coincidence. If it fakes it for root r times log n different A's, all simultaneously, Agrawal, Kayal, and Saxena prove that's impossible. N must be a prime power. And prime powers can be ruled out separately by checking whether n equals any small a to the b. The whole proof depends on picking r correctly. Pick it wrong, the algorithm becomes exponential, or the converse fails. Pick it right, and everything works. The condition is technical but worth seeing. We need r such that the multiplicative order of n modulo r is greater than log squared of n. In words, when you raise n to higher and higher powers and take the remainder mod r, it takes more than log squared of n raises before you hit the same remainder twice. Why this condition? Because the proof uses introspective polynomials. Polynomials that, when raised to the n, behave exactly the way primes do. The set of such polynomials forms a multiplicative group. The group's size is bounded above by something involving r, and bounded below by something involving the order of n mod r. If the order is too small, the group can fit a composite n. If the order is large enough, it can't. The threshold sits at log squared n. How do we find such an r? We try them. 2, 3, 5, 7, 11. For each candidate r, compute the order of n mod r. The first r that satisfies our condition, we keep. The crucial fact, proved using analytic number theory, is that we don't have to try many. Among the integers up to log to the fifth of n, at least one r will work. So r is at most polynomial in log n. The whole search takes polynomial time. Once we have r, the rest of the algorithm is straightforward. Loop a from 1 to floor of root r times log n. For each a, check whether x plus a to the n is congruent to x to the n plus a modulo x to the r minus 1 and modulo n. If any check fails, n is composite. If all pass, n is prime. Here is where the magic compresses. Suppose all the checks pass. We need to show n is prime. The argument runs by contradiction. Assume n is composite, and let p be a prime factor of n. We construct a multiplicative group inside the polynomial ring mod p, mod x to the r minus 1. We'll show this group is too small for n to be a non-trivial factor. N must in fact be a power of p. Define a number m to be introspective for a polynomial f if f of x raised to the m is congruent to f of x to the m modulo x to the r minus 1 modulo p. The condition that all our test polynomials, x plus a, satisfy the identity is exactly the condition that n is introspective for each x plus a. The introspective numbers form a multiplicative monoid. If m and m prime are both introspective, so is m times m prime. So the set generated by p and n, every product of powers of p and n, is introspective, reducing modulo r. This set has size at least the multiplicative order of n times p modulo r. Since the order of n mod r already exceeds log squared n, the multiplicative semigroup is large. On the polynomial side, the set of polynomials in our quotient ring fixed by every introspective number forms a multiplicative group, call it G. By a counting argument involving roots in the splitting field, the size of G is at most n to the root of t, where t is the order of n mod r. But we can also count G from below. Every product of x plus a's, for a in our test range, is in G. There are root r times log n such a's, and the products generate at least n to the root t elements. The two bounds collide. The lower bound, working out the algebra, exceeds n to the root t. The upper bound is bounded by t to the root t. The only way to reconcile them, given the size of t, is to force n to lie in the multiplicative subgroup of integers generated by p mod r. That happens precisely when n is a power of p. N is a prime power. We rule out prime powers by an upfront check at the start, so n must be prime. The whole proof, group theory counting a single polynomial identity, fits in 3 pages, 8 pages with prelude. The original AKS algorithm runs in time soft O of log n to the 15 halves. After Lenstra and Pomerantz applied a tighter analysis, the bound dropped to log n to the 6th. Agrawal himself conjectures the truth is closer to log to the 3rd. Compare this to Miller-Rabin, log to the 3rd per round, with vanishing error. AKS is slower in practice. Cryptographers use Miller-Rabin and elliptic curve methods, not AKS. The algorithm is too clean, too proof-shaped to be efficient. But that wasn't the point. The point was that primes finally joined the official list of things you can decide in polynomial time. The complexity class P got one citizen larger. A 30-year-old open problem was closed by a paper that 2 of the 3 authors had not yet finished their PhDs to write. The proof technique introspective polynomials in a quotient ring opened a new corridor in algorithmic number theory that's still being walked through. There's also something worth saying about who solved it. Manindra Agrawal was a tenured professor. Fine. But Neeraj Kayal and Nitin Saxena were students who had just finished their undergraduate degrees. They had taken Agrawal's algorithms class, gotten interested in the problem, worked on it for 2 years, and produced one of the most beautiful proofs of the 21st century. Both went on to win the Gödel Prize, the Fulkerson Prize, and faculty positions at top institutions. The paper itself, in subsequent editions, runs less than 10 pages. Sometimes the simplest path is just hidden a little higher up. Fermat had the test on numbers. AKS lifted it to polynomials, 3 centuries between them. The lift was waiting.